It's a great honor to be here at the Chicago University Conference. I know Spencer, the guy who's organizing this, one of the organizers, and I also know I'm seeing a few of my former students from Northwestern, so that's exciting. I'm now on leave of absence, and seeing former students is a great thing. But given that the audience is not so big, maybe you guys quickly tell me, is anybody here else from Northwestern? You know Chicago? Northwestern? Yeah, you look familiar. DePaul, okay, and you?
University of Chicago.
University of Chicago. Okay, so we have Northwestern, DePaul, and you have Chicago. Very interesting. You guys should talk to each other, it's not a big deal, so that's fine. Good. So I'm a professor of computer science at Northwestern University, but currently I'm on leave of absence doing this startup, blockchain-based startup. So I'm going to talk about that a little bit, and I'm going to talk in general about scaling problems for blockchains and stuff like that. So let me quickly, if this is going to work, maybe like this. Okay, what is the problem I'm talking about here? So the problem is, I hope I'm not going to need to spend a lot of time on this particular topic, because you all should be convinced that this is really indeed a big problem. So what is that? Well, one of the largest barriers for blockchains and their deployment is the lack of scalability. Okay? What does that mean? Well, that means Bitcoin, after all the hype and all the things that people are talking at different places and locations, Bitcoin today does 3 transactions per second. Okay. And Ethereum does 10 transactions per second. Okay. And I'm sorry, but that's where we are. Okay. There's a lot of hype on like, hey, it's gonna be a great thing. The best thing after the skyrocket ever developed is going to be blockchains. Well, if it can't scale, then it's not going to happen. Okay, and I'll just give you a few examples to show that there indeed is it's going to be necessary for blockchains to scale if we want it to be a mainstream technology. So, credit cards such as Visa process 5,000 transactions per second. It's huge, orders of magnitude bigger than what these mainstream blockchains actually give. If you take the number of cars in US and you assume each will fill a tank once a week, only once a week, just for that you need 450 transactions per second. Just for that. Forget about cars in China, forget about cars in Europe and elsewhere in the world. This is just for cars in US once a week. Okay? Take the number of vending machines in US and assume each is used 4 times a day. 4 times a day. By whoever passes by. Just for that, we need 1,000 transactions per second. Okay? And so at this point, it is a little bit embarrassing to talk about machine-to-machine communication and global micropayments, all the cool things that you keep hearing. Whenever you hear about blockchains, you hear about some fancy new world and some hundreds of thousands of transactions per second. And it's really embarrassing to talk about that in the world where we have 3 transactions per second on Bitcoin's chain. Okay? So what we are doing at bloXroute, we're trying to solve this problem, and not for just for Bitcoin and just for Ethereum, but for any blockchain out there, any consensus system, we want to give scale to such a system. Okay? And so we are not a blockchain. Okay? We are a networking infrastructure that helps blockchains to scale. Okay? So, but let's go to the beginnings. Okay? I'm still a professor, so I have this desire to go like, hey, let's simplify things. Let's go from scratch from point 0. Okay? And so let's take a look. I keep saying, hey, it's 3 transactions per second. Where does that come from? Who invented the 3 transactions per second? Why is it 3 transactions per second? Why it's not 7 or 55? Right? So let's take a look. So a Bitcoin transaction is 540 bytes. It goes up and down, but this could be taken as an average number. Okay? And then in Bitcoin there is this parameter which is the block size, and I'm not gonna explain how Bitcoin works. I assume you guys know that, but I mean this is that's what it is. So the block size is 1 megabyte, and it comes up every 10 minutes. It is mined by one of the miners that sits someplace in the world. Okay? And so if you put these numbers together, if you want to if you want to represent this 1 megabyte in terms of transactions, 1 megabyte divided by 540 bytes, that gives you roughly 1900 transactions. Okay? 1900 transactions divided by 10 minutes. If we turn now 10 minutes into seconds, this would be 600 seconds. No wonder. And if you divide these two things, 1900 with 600 seconds, you end up roughly at 3 transactions per second. Okay. This is where 3 TPS come into play. Okay. But now, just looking at this particular slide, we can see that 3 TPS comes is directly dependable on this particular relationship here. Number of transactions divided by the time interval. And hence, quickly, an idea comes to mind, you know what? Maybe we can fix this right away, right? If we tune these numbers a little bit, like, hey, 1900, let's put it to some bigger number, and decrease the interblock time, maybe that's the way to go, right? And so this is my next genius idea, which is, hey, let's do 300 megabytes every 10 seconds. Maybe we just now solved the blockchain scalability problem, and we can all go home and have fun. It's going to be a great day, and go back to Spencer, ask money back from Spencer, saying, hey, dude, thank you so much for all of this, but we're not going to go home because we just fixed the problem. We're so happy. Tomorrow will be in the news, so we're sorry we want our money back. Okay, I'm going to talk to Spencer later on. Maybe that's going to happen, but likely not, because he can't return the money. But going back to the seriously, why not do something like this? What's the problem? I'm a professor of computer networking is my field, and I'm saying, like, dudes, this is not going to fly. This is not easy to be done, because if you have nodes all over the world that needs to send this much amount of data to every single node, it's not going to be as simple. However, the blockchain space is dominated by cryptographers, and somehow these guys skipped the computer networking classes. And so they said, no, the internet is this cool thing, you just send and it works just fine, it's beautiful, right? I just watch YouTube, it works fine, everything is going to be great. And they did this on their own. So I'm not going to name a blockchain, but there was an example where people said, you know what, let's send 30 megabyte blocks, it's going to be just fine. The internet is a beast these days, it's 21st century, everything is going to be fine. And then what happened is that a 30 megabyte block was propagated. After 20 minutes, it reached another byte. Okay? And people started asking themselves, like, what? How could this be? Like, it's just 30 megabytes of data. How come it came so late at some other location in the world? What can go wrong? And at this point, I have to explain. I have to go back to ECS 340. I know you were there when I was talking about it, but I'm not sure about others. So let me explain what can go wrong. And my thesis is that there are 1,000 places where things can go wrong when you're trying to do these things on the public internet. And one more note, please feel free to interrupt me if there are any questions. That's typically a much better scenario, so feel free to raise your hand in case something is unclear. I'm going to feel like I'm back in the classroom. Okay? Okay, what can go wrong? 1,000 things can go wrong when you're sending a large chunk of data from one point of the world to another point of the world in a peer-to-peer fashion. What does that mean? So here is the famous miner who just mined one block, and it needs to send this block to its peers. Assume here I'm showing 3 peers, because the picture will be busy. In the real world, it's more than that, it's typically 8 peers. Okay? So this guy needs to send this to some number of peers. And so what happens is people think like, oh, there is a single connection here. Yes, but a single connection between yourself and any other endpoint on the internet consists of multiple different entities. You have autonomous systems, you have traffic flowing in these autonomous systems, and so the bad news in networks is that the worst component on an end-to-end path is the one that determines how good or bad your connection is going to be, right? So what does that mean? Well, if there is some network on your end-to-end path that is so thin, well, the most you'll be able to send is through this particular thin connection. Okay? If somebody is watching YouTube or Netflix and is downloading huge amounts of data, that will interfere with your desire to just send this block to somebody else on the other part of the world. Even worse than that, these guys, because Bitcoin is a system and other cryptocurrencies are such systems where you don't want to send this to your neighbors, but you really want to randomize who you are sending to because that gives a better security property. So these guys are likely, one is in China, one is in Europe, one is who knows where. Okay? So just in this particular case, if there are 10 links between you and the other end, there are 10 places where things can go wrong, right? If you have 10 connections to these other nodes, 10 times 10 is 100. Okay? 100 places where things can go wrong just for a single miner to send to its peers. Now this is just the beginning. There's 10 to 15 such hops for this piece of information to reach everybody else, right? Because in the first hop you send to your peers, then your peers send to others, then these others send to others, and it takes 10 to 15 hops to do this. Less or more, but it needs some time. So multiply 100 times 10, 1,000, okay? And I'm gonna add even more trouble to this. If you look at this particular setup, not only do you depend on the network in between, but you also fundamentally depend on the peers themselves, right? Because when the information, when a block or whatever transactions comes from here to the middle point to here, if this guy is not set well, and you're connected to it, this guy can slow down the entire communication, right? Nothing to networks could be fine, but you're fundamentally dependent on this particular peer, which is somebody setting their machine and they just didn't set some parameter well, and I'm sorry, but your block is not going to propagate as it should have in such a particular scenario. Okay. And this is a bit kind of tricky to an extent. Why is this tricky to an extent? Well, I hope I just convince you that sending a block or some large amount of data from one endpoint to another, to a set of other endpoints on the internet is a big problem. Like it's a huge problem. And then at the same time, YouTube, for example, is streaming terabytes of data every single second. We are using the YouTube, and then, I mean, the stream is often pretty good, and when it's not good, we are all concerned, like, hey, I think that would say that
Don't worry about it.
No, I'm not worried. I'm just trying to understand if there is any pattern when it's going to stop or something. But thanks to I think this would be the half of my talk, which is telling me I need to hurry up because I have other things to say. But what I'm trying to say is this is the way it is. I mean, I didn't tell you anything that is not the way it is. But the question is, like, why do we have to have such a flaky networking communication for blockchains? When YouTube, which is sending terabytes of data every second, and nobody blinks an eye. Everybody is like, okay, that's the way it works. When we see that the stream is delayed, you see that circle, and it's telling you rebuffering or something, we are all like, hey, what's going on with the world? Like today, like, how come it's not working fine? So, how could it be that in this world, sending 1 megabyte to all nodes is a big problem, and sending terabytes of data in the other world is a solved problem. Okay? So here I'm coming back to what bloXroute is doing and how we're doing it. So basically, what we are doing is we are building a YouTube for blockchains, right? We are saying, like, hey, the way that the networks work for blockchains currently isn't good. We want to fix this. How do we fix this? Well, we want to add a dedicated, neutral, I will explain what that means later, network infrastructure for blockchains, so that it can look like when you are using YouTube for streaming videos. Okay. How do we do that? Let me quickly go through an example, going back to the 30 megabyte block that I just explained that has trouble going through the peer-to-peer network, and I'm going to explain how do we do that in our network. So in our world, an important thing that we are doing is that we are using and we are utilizing this idea of transaction caching. What does that mean? Well, in Bitcoin and many other blockchains, transactions are first collected by the miners. Okay? Hence, all the miners have access, they live in the mempool. Okay? And once somebody mines a block, then that block consists of these transactions which are then sent to the network. So what this is telling us is that the same piece of information, a transaction, is sent twice and received twice by each node. Right? It is initially sent by whoever created the transaction, and it's distributed to peer-to-peer network to all the nodes. And at the same time, once the block is created, this same transaction is placed in that particular block and is sent to everybody else. So what we are doing, what bloXroute is doing, we are basically saying, listen, if this transaction is 540 bytes, we're going to use some short identifiers within our network that would help significantly reduce the amount of data that needs to be sent once the block is sent from the miner to everybody else. Okay? So this itself gives more than 100x of compression, which you can't get with the regular data, because with regular data, whatever algorithm you use, you can't get to this level of compression, because it's not going to fly. Okay? But here we are using these things so it flies in our case. So in the case of a 30 megabyte block that needs to be sent, in our world, internally, this becomes 222 kilobytes. Instead of downloading a huge file, you have to download a small web page. Right? So we are zipping significantly the blocks once they come into once they are sent to the network. And so these red dots are our service. Another thing that we are doing is cut-through routing. Cut-through, again, for those who took my networking class, would know that it's this has been used in switches for decades, like easily 30 years ago. People started using cut-through routing. What is that? Well, once a switch starts receiving a piece of data, it doesn't have to receive the entire message. It can already start streaming this data to the other endpoints. Okay, so this is a very well-known technique. So what we are using this for when blocks and transactions are sent. So how does it work? Here is an example. This is a node sending a block to bloXroute, and hence there is some delay. It doesn't come quickly because, I mean, necessarily if these are not on the same exact location, there's going to be a small delay. Then this block is received by the bloXroute server, and before all the bits are received, this guy already starts streaming to the other nodes. Okay? And so what can happen is that this initial node still didn't finish sending this entire block. This other guy at the other side of the world sometimes can actually start already receiving the bits of this particular block. Okay? So this is further helping with scalability. And so to summarize, what we are doing, we are building a broadcast layer for blockchains. Okay? And instead of having 1,000 places where things can go wrong, that I explained how it works with the peer-to-peer, here we have 3 places where things can go wrong, and we are making sure it doesn't happen. Okay? So the first place is it goes from a miner to a local bloXroute's server. Here, because these guys are very close to each other, because we are trying to build a very wide network. It's not as big as Akamai's, but it's fairly good and wide network. So this connection is fairly well provisioned, and this guy has enough capacity to serve it. Within our cloud, we are capable of making things good. And then finally, at the other edges, at the edges of the network, you can see that there is, it's the same thing like with the first hop. Okay? And one very important piece of information, unlike in the peer-to-peer case where you're dependent fundamentally on what others are doing, if somebody has a buggy machine or some other, you're connected to a miner that is not really delivering. Here, you can see that every single node is connected to every other node with a single hop. Right? There are no miners in between here. This guy sending whatever it sends immediately reaches all the miners, and this is what happens. Okay. 2 days ago, after 2 years of hard work, we were capable of showing the scaling results that of scaling Bitcoin. Okay. So what we did is we took the Bitcoin code, okay, and we put it on top of bloXroute. Okay. And we were capable of moving the thing to about 1,000 transactions per second. Okay. And we are thinking, listen, if we're capable of doing this with the simplest blockchain, we should be able to do much better with others, but I'm gonna leave that for the rest. So in this particular case, we had more than 300 nodes, 30 miners, and all of them scattered around the world in Asia, Europe, and North America, and we were capable of pushing 500 to 100 megabyte block every minute. But remember, because we are using compression, this is feasible because of the things that I explained. I'm super proud of this particular result, and it may look easy, like, oh, of course, now that we know how it works, but it takes a lot of engineering effort to make this happen, and we made this happen. Please go, yes?
That was core, 1 megabyte blocks, not like Bitcoin Cash or anything?
No, we did this using our own testing. So basically, this is nothing to do with the mainnet of any of these particular.
I was asking what size blocks you were.
50 to 100 megabytes. Okay, so let me just check how are we doing with that. So I think we're doing fine. Basically, this is all very nice. I mean, oh, okay, you have a YouTube for blockchains, problem solved. Not really. I mean, one part of the scalability part of the problem is solved. But when you solve one problem, you wake up another problem. Okay? So what is the other? I mean, this is how it works in research in general. What is the problem that we woke up? Well, blockchains are these distributed systems where you have endpoints, nobody owns the system, and it's completely, everybody is autonomously checking transactions and so on. So if you throw in this powerful I'm going to call it powerful, a bloXroute network in between, then the centralization, if this network is not designed properly, then the centralizations go through the window. Why is that? Well, if you have a network that is looking at the transactions and blocks, and it can say like, hey, I don't like this transaction, I like this block, then that's no longer a blockchain. I'm sorry to say that. Okay? And we were aware of this from the very beginning. Okay? This is why when we started designing this particular network, and this is actually a PhD thesis by my former PhD student, Uri Klarman, who is currently bloXroute's CEO. He figured out like, hey, we have to do this right, and we have to make this neutral by design. What does that mean? In short, that means that the network itself is incapable of censoring information going through the network without the nodes being capable of detecting them. This is the guarantee that we provide. And I'll just quickly give you one of the examples here, one of the mechanisms, which is encrypted blocks. What does that mean? If the network knows which transactions are in the block and so on, then what can happen is an authority, FBI, and I'm not inviting anybody, can come to us and say, hey guys, these are some really bad folks doing some really bad things, so please, whenever you see this particular address, don't push this block through the system because bad things are going on here. Okay? Our answer to them is, dear whoever, we equally dislike the bad guys and we would be excited to help, but unfortunately there is nothing we can do to help here, not because we don't like, but because we can't see what is inside these blocks. Why is that? Because by design, a block before being transmitted through our network is encrypted. Okay? So what the network gets is an encrypted piece of data that it sends to everybody else in the system. Okay? Only once the data has been transmitted to everybody does the source node releases the keys to the peer-to-peer network. Now these keys are very tiny and small, and they can propagate quickly through the network, and then the other nodes decrypt this thing and look into the block. Okay, so this is providing a guarantee not just to us, if anybody comes to us, but this is providing guarantee to others in the system so that we can't do anything with them. And we have other mechanisms such as indirect relay and auditing with test blocks, but I'm not going to dive into that because we don't have time. But this is a very, very important piece of the design because it is essential in this particular set. Now let me see how we are working with time. Deployment-wise, we are talking to the mining communities around there, throughout the world, and we are making an effort to put our system in their hands. Okay, how is that going? What do miners get by deploying bloXroute gateways? I didn't explain what a gateway is. It's my bad, but basically we put a small piece of software on the miners so that they can actually get access to our network. On one end, gateways speak the native blockchain language, and on the other end, they speak the bloXroute language so that they can send data to our blockchain distribution network. So what the miners get, they hear about transactions sooner and start the mining faster. So having information ready is good, because if you know about the newest transactions, you're capable of creating a block that picks up more fees than if you don't have this information. At the same time, when you send a block, if it's sent quickly and it's going to be at other miners within hundreds of milliseconds, that decreases the probability that particular block is going to be forked because the information is actually there already. And so currently we are basically deploying this. I'm going to skip our business model for two. Initially, I thought it's important to talk about this, and it depends on what you're doing. If you're a student doing research, you shouldn't worry much about who pays whom and why. If you're doing a company, particularly in crypto, you really want to think about this and take care about this. And so this would be my advice. So I'm going to skip through this because we really don't have time. We are located in Evanston. As you can see, Chicago is a small city south from Evanston. This is the center of the world, and then if you go 10 miles south, this is where we are now. There is some small city there. Currently, our headquarters are it says in Chicago, it's in Evanston. Okay, and so of course we are hiring. So if any one of you is interested in coming, joining, learning, or just talking to us, I mean, we are super open to that. I'm going to skip this. What's next? So as I told you, we're deploying currently with a bunch of miners. Currently, we're doing tests on Bitcoin Cash testnet, and we have a number of mining pools, BTC.com, Pool, and Raw Pool currently, and others. We are planning a test with Ethereum for June 2019, and in Q3 2019 we're going to launch our mainnet, so anyone will be able to install a gateway on their nodes, even if they're not miners, and then get access to the information coming from any particular blockchain. So this may actually be useful for research, even if you are not going to do any mining or anything, but just like measuring and understanding, getting the information quickly may be useful for research. So with that, I'm going to stop. I'm just going to say that we are trying to scale all blockchains because the common problem for all blockchains is how do you send information from one node to all other nodes, and doing this effectively in a neutral way is something that we can help with, and that's what we're doing. That said, I'm going to stop here, hoping that I'm not going to get interrupted anymore by this exciting clock, which I'll look into after this talk. Thank you so much.